Okay, so at the end of the last lecture, we talked about the four factors, the four things that we look at in trying to analyze or interpret an NMR spectrum. And they are the delta value of the chemical shift, the integral, the multiplicity, and the coupling constant. We did say that we will not spend a lot of time on the coupling constant. It is not unimportant, but for intraorganic chemistry, it's not a critical data point. So we talked at length in the last lecture that a chemical shift really is appropriately named. It tells us how the frequency of the proton under consideration has shifted away from the reference as a consequence of the chemical environment of the proton. So it's a chemical environment causing a shift from the reference. But it turns out that the chemical shift depends upon several different factors. It depends upon induction. It depends upon resonance. It also depends upon something called anisotropy. And in the last lecture, we did show how the inductive effects play a role in the chemical shift. And what I would recommend is you go back and look at the previous lecture when we talked about the effect of chlorines, having fluorine, chlorine, bromine, I don't know if you mentioned iodine on the chemical shift, and what's the impact of having two chlorines, and so on. And I just feel compelled. So H attached to C attached to Cl, this shows up at about 3.5. H attached to C attached to two Cls, that shows up at 5.8. H attached to C attached to three Cls, that shows up at about 7.2. So clearly, the more chlorines you have attached to the carbon, the alpha carbon, the more they bleed electrons from the H, the more they de-shield the H, and so the proton moves progressively downfield. If I had an H attached to fluorine, H attached to carbon attached to fluorine, that shows up at about 4.5-ish or so. But clearly then the impact of two chlorines beats the impact of one fluorine. And then if it was bromine, the number drops to about 3.0. So H attached to C attached to bromine, that's only about 3.0. So you can see the impact of electronegativity, you can see the impact of the number of those groups, and so on. So that's induction. But what about resonance? How does resonance play a role in the chemical shift? And there are two nice examples of that. So I'll go here. There are two nice examples of that. And the first one is if you look at the chemical shift of an aldehydic H. So we say H attached to C attached to O, and that H appears at about 3.5. And that's intriguing because that's the same number that H attached to C attached to Cl shows up at. And that's not surprising because Cl and O have almost the same electronegativity. So obviously the impact on the delta value of H should be pretty much the same. But if I look at the H attached to C of an aldehyde, that value jumps all the way to about almost 9, or what does it say, 9 to 10? Aldehydic H's are 9 to 10. So I'm going to pick a number in the middle and call it 9.5. Now, it turns out there are two different factors in operation here. But certainly, there's a huge difference. And considering that the entire spectral window for proton NMR is 12 units, run from 0 to 12 for most organic compounds, that difference is half the entire window. I mean, that's massive. Well, why? Well, one factor is, in the alcohol or the ether, whatever, this O is pulling electron density from the H by induction. Induction is electron drift along a sigma bond, along a sigma framework. Well, that's happening here too, right? One of these bonds is a sigma bond. Let's pick the one on the left. And so by all means, this effect is also operational, right? It's exactly the same effect that's operational. But carbonyl compounds, as you well know, can be represented by a resonance form in which there is a negative charge on the O and a positive charge on the carbon. Which means then that this H of an aldehyde in that resonance form is actually next to a carbocationic carbon, right? To some extent. Which means the pull of this carbon is much, much greater than the pull of that carbon. So that the resonance effect that is true for all aldehydes causes the delta value of this H to be much higher because the H is more deshielded than you'd expect by simple induction. So operational in the aldehydic H delta value is induction, but there's also resonance, and as we'll see in a second, there's a third factor. How else does resonance play a role? Well, let's imagine I have this compound. So let's say I have this that compound. It turns out that, and we'll see this in a little bit, the H's that are attached to a carbon, attached to a carbonyl, show up at about a delta value of about 2.4, right? So H attached to C, attached to an aldehyde, a carbonyl, carboxylic acid, aldehyde, ketone, they show about 2.4. As you go a little further away, the inductive effect of that carbonyl group, right? Because I can draw a positive charge here in a resonance form, or I can say, that O is now further away. The inductive effect is less, because either way you cut it, you remember from your Gen Chem, and certainly from Organic 1, that the inductive effect is very strong, or can be very strong along the first bond. It's modest along the second bond. It's weak on the third bond, and it's basically non-existent beyond bond 3. So, if I say the effect is due principally to the positive charge on that carbon, which is not entirely wrong, there is a strong effect here on bond 1. This is bond 2. This is bond 3. So the effect here is going to be quite weak. And this might show up about 1.5, a delta value of 1.5. But once I get to here, that methylene group shows about 1.2. 1.2 is the chemical shift of an unperturbed methylene. A methylene where the H's are neither shielded nor deshielded. So I would see this at about 2.4 because we're close to the carbonyl group. Or if you want, we're close to the O, right? And so we're within the inductive effect, right? 1, 2 bonds, 1, 2, 3 bonds. More correctly, the large delta positive charge of that carbonyl. So we're 1, 2 from it. Here we're 1, 2, 3 from it. So the effect is very small. And really, if you're 1, 2, 3, 4, you don't feel it at all. So I expect that to be 1.2, that to be about 1.2, and so on and so on and so on. But if I look at this compound, I make this compound the alkene, my expectation would be, well, certainly the H, which is more proximal to the carbonyl, this H, let's call it HA, I'd expect that to have a larger delta value than HB, right? Because after all, if I call this HA here and HB here, HB in this one is further removed from the carbonyl. The inductive effect is less. So what I see in this case is the delta of HB is less than the delta of HA. And that makes perfect sense. That's an inductive effect. That's not true here then. If I look at this, the delta of HB is actually quite greater than the delta of HA. Well, how is that possible? Right? Clearly by induction, this should have a lower delta value because it's further away from the positively charged carbon. Well, the reason is that system has resonance. So I can take that compound and I can draw resonance forms for it that look like this. And in that resonance form, I have my single bond O, and I've got a positive charge on this carbon. So now HB is attached to a carbon for which I can draw a resonance form that has a positive charge on it. So this H is actually now bled of electron density more than HA because there are no resonance forms in which that carbon has a positive charge. So yes, induction is operational, but resonance beats induction. So the delta value of HB is actually much higher, by a good unit or more, than the delta value of HA, and that's a consequence of resonance. And if I had this compound, if I had this one, what I would find is that this H has a higher delta value than this one and that one. And this one, because I can also draw resonance forms that include it, right? I have a plus charge here too. This H, although it's far away from the carbonyl, would still have an unusually high delta value because of resonance. It will be slightly less than this one because this one has some induction, which this one doesn't. Okay, so we can look at the effects of induction and resonance on the chemical shift. The other factor is anisotropy. And anisotropy literally means that it is oops, I spelled this wrong. This is anisotropy. So what it means is that the form tropos is uneven in space. So anisotropic means that the form tropos is uneven, aniso, right? And this is a spatial feature that is a consequence of pi systems. Now, that's not entirely true. It turns out that there's also some weak anisotropic effects for sigma systems. You see that a lot in cyclohexanes. We're not going to talk about that. We're going to limit our discussion to what happens in pi systems. So if I look at a carbon-carbon, if I look at a double bond, yeah, let's go here, because you guys can rewind and so on. So this is fine. If I look at a double bond, so let's look at a C double bond C. This is true for C double bond O as well, and that gets back to the point I was making earlier. If I apply a field, so this is my B naught, the pi electrons, if you remember, they're more loosely held than sigma electrons. So those electrons are going to respond a lot more readily, a lot more, to the applied field than would sigma electrons. But the way they respond is to, and there are studies that show where you can map the field, okay, where you can map the field. So what happens is that if I apply my field this way, the electrons respond by generating a current that acts in this direction. Let me just work this out. So what I get is my field operating in this direction. So this is why it is uneven through space. So in other words, the induced field for pi electrons doesn't act in the same direction. So they go this way. So at some parts of the structure, they are parallel to the field. In other words, the induced field is parallel to the applied field. But in some parts of the structure, the induced field is in opposition to the applied field. So what this means then is that the impact of the applied field is different in certain places. Because obviously, when it is parallel to the field, the B effective is large. And we saw earlier that when the B effective is large, so like with the silicon case, where there was a large amount of electron density, so the B effective, which was the B naught minus the B induced, when this is a large number, that the delta value was small. Okay? So when the induced field is acting in opposition to the applied field, then the delta value is small. But in a case like H attached to F, right, where B effective, where there's a small amount of electron density around the H, the B induced is low, and therefore the B effective is going to be larger, and that tends to a large delta value. So what this means is that H's that are attached to the vinylic carbons, the carbons of the double bond, actually show up in a region where it is where the field is acting in parallel, which means the B effective, which is equal to the B naught plus the B induced, that number is large. If the number is large, right, what we said here, when the induced field is large, we have a low B effective. A low B effective gives a small delta value. But if the B effective is a large number, right, then what that means by extension is that delta value is going to be relatively large. So H's attached to the vinylic carbon show up between about 4.5 and about 6. Let me see what numbers this suggests. It shows up between, so H attached to, about 4.9, but they say 4.5 to 5.9. That's close enough. So the H's attached to vinylic site are relatively de-shielded. Now, let's think this through. H attached to a carbon, an sp3 hybridized carbon, right? They typically show up between 0.9 and about 1.5. That's typically where those H's show up. If it's methyl, it's 0.9. Methylene, 1.2. Methine is 1.5. But these are low delta values. The sp2 hybridized carbon is a little bit more electronegative than an sp3 hybridized one, but not enough to cause a 3-unit difference or more in delta value. That is a quarter of the entire range. The reason they're so high is because in this region of space, the induced field acts in support of the applied field. So the B effective for these is unusually large, therefore the delta values are unusually high. So what many people do is they divide the molecule into what are called cones. And I'll draw a cone in red, and the cone looks like this. So anything that is in this part is in the de-shielding cone. Right? This is de-shielded. But obviously now, when the circulation creates an induced field that acts in opposition, these are what's called a shielded cone. So if you are a proton that finds itself in the shielded cone, your delta value is going to be very low. If you happen to be in the de-shielding cone, your delta value is going to be very, very high. Okay? And obviously, by the way, you know, I can see this as 4 different cones. There's a cone here, there's a cone here, a cone here, and a cone here. There's a funny story about an organic research project where they were trying to figure out the structure of a compound. And they had done the elemental analysis and realized the compound had X hydrogens. But when they ran the NMR, they were only finding X minus 1 hydrogens. So they couldn't figure out where the other hydrogen was, because they could account for all the other H's in the molecule except for 1. Turns out the molecule was an alkene, but it was a very rigid multi-ring system. And it was so rigid that you ended up having, this is going to be a really bad structure, but it ended up being some sort of weird ring structure. Right? This is a really bad example. But one of the H's in the molecule ended up in the shielding cone. And so what happened was the chemical shift of that H was below 0. Because that H just happened to be in the shielding cone, and it ended up way below 0. So when they were running the NMR between 0 and 12, that H was invisible. It fell outside of the regular spectral window. But when they extended it to -2, they picked up the proton. So, which goes, you know, what you do with the NMR, or for that matter any technique, you kind of need to know what you're looking for in order to best set up the experiment. So you don't want to just go blindly, right? If you live with a rigid vinyl system, you may want to expand your spectral window. Perchance, an H ends up in a shielding cone. Now, remember we said that the carbonyl, the aldehydic H, has an unusually high delta value. And we said one reason was induction, because of the sigma bond attached to O. One was resonance, right, which created a delta plus charge here. The other one is anisotropy. Because the anisotropic profile doesn't matter whether it's C11O or C11C. So your de-shielding cone looks like that. So the aldehydic H's are in the de-shielding cone. Which is, so if you add induction, which might account for 3.5, you add resonance, which gives you a positive charge on this carbon, right? Which accounts for some number of an increase, and you add anisotropy, which is potent. The combination of all three makes the chemical shift of an H attached to a carbonyl carbon very high. So you tend to find these around, you know, between 9 and 10 ppm, very high on the window. There is also an isotropic effect for alkynes, which accounts for why the values for allyl H's are relatively high, about 1.5. And H's that are attached to the allylic site are about, the acetylenic site are so high because they also find themselves in a de-shielding cone. So that's an isotrope. Okay, good. So we talk about chemical shift and the number of things that affect it. Let's talk about the integral for a minute. So what do I mean by integral? Well, it turns out that fortunately we can determine the relative numbers of protons under consideration. So let's make life very simple. Let's imagine I have the different isomers of butane. So let's say I have butane and I have 2-methylpropane. If I run the NMR of butane, I will first of all see, I should have had something else in here. So I'm gonna say 5. I could have said 0, but I'm gonna say 5, which is the number of signals. That's important. So I'm gonna leave this out, but I'm gonna do this. And I probably should have started here. The number of signals tells us the number of different types of protons in the compound. Now, I'm going to add a caveat. Because the spectral window for proton NMR is so narrow, 0 to 12, it is possible, and it happens quite often, that 2 different sets of protons that have very different environments will end up at exactly the same chemical shift. Because remember, the chemical shift is a confluence of induction, resonance, and isotropy. And induction itself depends upon which heteroatom, how many heteroatoms, and how close they are to the H. And when you add all those things together, it can happen by weird coincidence that an H in one environment has the same chemical shift as an H in another. So it is possible in NMR that 2 or sometimes more different types of H's show up under the same signal. So when I say the number of signals indicates the number of different types of protons, that is the best case scenario, right? That's the best case scenario. So if I look, for example, at, and you know what might be a better example, is to look at the pentanes. Let's do the pentanes. So if I look at the pentanes, I'm going to take N-pentane, 1, 2, 3, 4, 5. I'm going to take iso, and then I'm going to take that compound. If I look at pentane, how many different signals will I see? And the answer is, well, what you do is you read across the molecule. So I have a methyl group attached to a methylene, a methylene, a methylene, and a methyl. Well, that's true here too. A methyl group attached to a methylene, a methylene, a methylene, and a methyl. So this gives me the same signal. I have a methylene attached to a methyl and a propyl. Well, that's true here too. I've got a methylene attached to a methyl and a propyl. And I've got a methylene attached to 2 ethyls. So there are 3 different signals in this compound. They give me 3 different signals. Here I have a methyl attached to an isobutyl. Methyl attached to an isobutyl. I have an H that is attached to a gem dimethyl. And again, so I'm highlighting the carbons, but I really mean the H's on the carbons, right? Here I have a methylene attached to a methyl and an isopropyl. And here I have another methyl, but that methyl is different from the others. This methyl was part of a gem dimethyl unit. This one is not. So I would get 1, 2, 3, 4 signals from this compound. This one, which really is the same as this, right? All of these H's are identical. CH3 attached to T-butyl, CH3 attached to T-butyl, CH3 attached to T-butyl, same thing here. So I get 1 signal for that compound. So the number of signals tells me at best the number of different kinds of H's. Okay, so let's do that. What about the integral? The integral tells me the relative number of protons that gives rise to each signal. So if I look at this compound, I have 6 methyl H's 4 of these and 2 of those. So I would expect to get a 6 to 4 to 2 ratio, basically 3 to 2 to 1. So when I look at the NMR of this compound, I should see 3 signals. The integral is the area under the peak. And if I sum the area under the peak, the ratio of the areas would be 3 to 2 to 1. Here, I'd expect that to be 6 to 1 to 2 to 3. 6 to 1 to 2 to 3. So when I run the NMR of this compound, I expect to see 4 signals. And the ratio of the area under the peak, the integral, should be 6 to 1 to 2 to 3. If I run the NMR of this compound, I expect to see 1 signal. There's nobody else, so there's nothing to say about any relative peaks, right? I just see 1 signal. Because the integrals are relative to each other. The NMR will never tell you I've got 6 protons and 1 proton and 2 and 3. It'll tell you that's the ratio. Because your compound could have 60, 10, 20, and 30. So NMR doesn't tell you how many protons, it just tells you the ratio. Now, for a lot of the examples that you will get in this course, I'll tell you it's 6 H's, 2 H's, 3 H's, or 1 H. So I may give you that information because at this level, we would just like to give you the number of H's under consideration. So the chemical shift tells me the environment of the proton. The integral tells me how many protons give rise to a given signal. The number of signals tells me how many different kinds of protons we have. Multiplicity. So the multiplicity of a signal is information as to the number of neighbors a given H has. So whereas the chemical shift speaks directly about the proton under consideration, but takes into account who's around it, right? The integral speaks directly to the proton under consideration and tells me how many of them there are. The multiplicity speaks to the number of neighbors, and by neighbors we mean protons on the adjacent carbon. So I'm going to describe how that works, and then we talk a little bit about the consequence. So let's imagine I have an H attached to a carbon that has no H's on its neighbor. So here's my H. There are no protons on the adjacent carbon. Well, this proton has a certain spin. And let's say that spin, right, let's give it a certain magnetic field. Let's give it that designation. When I apply my magnetic field, that proton, the electrons around the proton circulate in opposition to the applied field. I create a B induced, I get a B effective, I get one B effective, and that H gives me one resonance, right? I get one delta E, I get one frequency, I get one peak. So this H shows up as a singlet, right? So it's a singlet, and I'm going to say S. If I have a compound where I have an H now attached, let's call this HA, and now there's an HB, in other words, I've got one H on the adjacent carbon, and I'm looking at HA. That's what I'm this is the one under consideration. HB has two spin states, because HB could either be parallel with the field, or HB could be anti-parallel with the field. I don't know which. So there's a 50-50 probability that when I apply my B naught, my applied field, HB, because it's in coupling distance, and I didn't mention that, but HB and HA can couple with each other. Because the spin state of the nucleus impacts the electrons in a covalent bond, which impact this covalent bond, that nucleus. So we're transmitting information about spin states from this nucleus to that one. Because we're in coupling distance, 1, 2, 3. That's induction, right? So when I apply my B naught, two different fields are felt by HA. One in which B naught is added to this spin state, one in which B naught subtracts that spin state. That creates two different delta E's, two different B effectives, and therefore two different delta E's. Which means this HA comes to resonance twice. And they will come to resonance in 50-50 because the likelihood of up or down is equal. So what I will get for HA in this scenario is a doublet. Well, what happens if I now have two HBs attached to, if I have two HBs on the adjacent carbon? Well, what are my possibilities for the states? Well, either they can both be aligned with the field, one can be up and one can be down, one can be down and one can be up, or they're both down. Right? Because I've got two HBs. So what are my options? They're both aligned with the field, which means they're both reinforcing the field. So when I try to get my B effective, that's the applied field plus these two things. One is up, one is down. They cancel. So what this H sort of feels is essentially the applied field. But there are two possibilities. Up, down, and down, up. But they add to the same thing. Or they can both be anti-parallel. Well, these represent three different options, three different spin states, three different states. But they arise in a 1 to 2 to 1 possibility. So HA comes to resonance 3 times. And what I see is a triplet that is in a 1 to 2 to 1 ratio. Now, this is important because if I ever asked you to sketch the NMR spectrum and you need to draw a doublet, I expect to see the two peaks that have roughly the same intensity. If I ask you to draw a triplet and you draw this, well, that's not a triplet. A triplet needs to be in a 1 to 2 to 1 ratio, right? Because that represents the reality on the ground. Those are the number of permutations for two spin states. Both up, one option. Both down, one option. One up, one down, two options. What if I had HA, but there were 3 H's on the adjacent carbon? So 3 HBs. Well, what are my possibilities? And my possibilities are that all 3 would be aligned with the field. Right? So I've got all 3 up, 2 up, and 1 down. And I'm going to do this systematically. I'm going to take the down one and slide it across until it becomes on the far left. 2 up and 1 down. 2 up and 1 down. These are the same. Well, these are equivalent. I could have 1 up and 2 down. Slide this one over. 1 up and 2 down. 1 up and 2 down. Now, these are equivalent to each other, but they're not equivalent to that set. And then the last option is they can all be down. They represent 3 different fields that HA will field. They are in the ratio of 1 to 3 to 3 to 1. So HA will come to resonance 4 times because they're 4 different fields. But the intensity of the peaks will be 1 to 3, 3 to 1. So something like that. So if I'm going to draw, and that's called a quartet, right? So my multiplicities can either be singlets, doublets, triplets, or quartets. Now, turns out, sometimes I have neighbors on the adjacent carbon, right? On a different carbon. And so what you sometimes get is a multiplet. So if you've gone beyond singlet, doublet, triplet, and quartet, but for example you have neighbors here as well. So if I had something like this, well then this HA is going to be a septet, right? Because I've got 6 neighbors. And so there's a point I missed. If I have 0 neighbors, so if n is my number of neighbors, m is my multiplicity. So n is the number of neighbors on the adjacent carbon, m is my multiplicity, the number of peaklets in the signal. If I have 0 neighbors, I am a singlet. If I have 1 neighbor, I am a doublet. If I have 2 neighbors, I am a triplet, 3 peaklets. If I have 3 neighbors, I am a quartet, 4 peaklets. So the rule for multiplicity is that the multiplicity is equal to n plus 1, where n is the number of neighbors. So 0 neighbors, 0 plus 1 is 1, I'm a singlet. 1 peak in the signal. If I have 1 neighbor, my multiplicity is 2, 1 plus 1, that means a doublet, right? 2 peaks in the signal, and so on and so on and so on. So this is the operating rule for what's called first order in MR spectroscopy, which is a simple scenario. All right. Okay. So, and then the last thing was the coupling constant, which I'm just going to leave out. It's not. We're not going to worry about that in any kind of length. Okay. So the last thing we're going to do before we end this lecture is to look at certain spectral patterns and certain telltale chemical shifts. So spectral patterns and chemical shifts. And so the next thing after this would be analyzing spectrum. So I'm going to say spectral patterns and chemical shifts. And really, what this is there are some spectral patterns that reoccur very often. So in other words, if you see them, they suggest this. And in the same way, there's some chemical shifts that reoccur over and over again. And if I see a chemical shift to this value, that means this. So that's kind of what we're going to do here. This is a very quick guide for when you first glance at the NMR spectrum. This is kind of what I'm looking for. These are the things that should jump out at you. Same way when you look at an IR, you might see a carbonyl band at 1710, that says something. If it's got a doublet at 2800, that's an aldehyde. So
So there's some quick hits to get from a spectrum. That's what we're going to be doing here. And so if I see, well, I'll just put the group. So if I see a singlet for 3 H's that screams CH3, right? That's fairly straightforward. What it also says is that whatever is here, this has no hydrogens. I know that because if it did, this CH3 would have been split into a singlet, doublet, triplet, quartet, multiplet. This X could be a carbon that has no H's. It could be a heteroatom, like O, so it could be an ether or an alcohol or so on. If I have a singlet for 9 H's, that screams T-butyl. Because all of these H's are equivalent to each other. And of course, their neighbor has no H's. So this screams of a T-butyl group. If I see a triplet for 2 H's and a quartet triplet for 3 H's, for 3 H's, and a quartet for 2 H's, and typically the quartet will be downfield relative to the triplet. This implies I've got an ethyl group. So presumably X is something that might be electron withdrawing, maybe. So the CH2, this will integrate for 2 protons, but because there are 3 neighbors, 3 neighboring H's, it shows up as a quartet. So I get a quartet for 2 H's. Now you want to be very careful. The multiplicity quartet tells me nothing about these H's. It tells me about the neighbors, how many neighbors I have. So a quartet tells me I've got 3 neighboring H's. The integral for 2 H's tells me that there are 2 H's in this carbon. So a quartet for 2 H's implies a CH2 attached to CH3. On the other hand, these 3 H's, right, will give me a signal that integrates for 3 H's, but it also gives me a triplet. And the triplet arises because there are 2 H's on the adjacent carbon. And if I use the n+1 rule, I've got 2 H's here. These will show up as a 2 + 1 with a triplet. Okay? So the triplet has nothing to do with the fact that there are 3 H's on this. Right? Because I can have a compound like this, CH3CH, right? Where this has 3 H's, but it shows up as a doublet. Because there's only 1 H. So 3 H's on a carbon doesn't give you a triplet automatically. It tells you it's going to integrate for 3 protons, but that says nothing about the multiplicity. So the multiplicity doesn't give you information about the protons you're looking at. It gives you information about the number of protons on the carbon adjacent to the proton you're looking at. Okay? And if I have a septet for 1H and a doublet for 6 H's, that screams I have an isopropyl group. So this H will integrate, this signal will integrate for 1 proton, but it has 6 nearest neighbors, so that's going to give me a 6 + 1, which is a septet, whereas these CH3s. There's 6 of them because they're identical. And they're in a carbon attached to 1H. So I'm going to get a doublet, 1 plus 1 is 2, which integrates with 6 protons. So these are the spectral patterns for aliphatic compounds. In other words, compounds that don't have, that are not aromatic. And we're going to do aromatic chemistry in a little bit. I'm going to extend this part here. So these are spectral patterns for aliphatic, meaning that they're not aromatic, right? I'm going to extend that. These are spectral patterns. These are for aromatics. There are several of these that we can look at. I'm going to limit it to just a few. If I have a benzene ring that is monosubstituted, first of all, the aromatic ring will integrate for 5 H's. Right? So I'm going to get an integral for 5 H's because I've got 1, 2, 3, 4, 5 H's on a benzene ring. So if it's monosubstituted, it will integrate for 5 H's. The spectral pattern will depend upon what X is. So I'll make it simple. If X is a group like methyl or ethyl, which does not push or pull electrons to any large extent, what you will likely get is a singlet, and it depends upon the operating frequency of the instrument. If the operating frequency is high, like in anything above 100 megahertz, that singlet gets teased out into several peaks for the ortho, meta, and para H's. Most of the spectra that you'll be presented with are run at 60 megahertz. At 60 megahertz, everything collapses, and so you won't be able to resolve this, the ortho, meta, and para H's because they're very close to each other. And so what you will see is a singlet. So you get a singlet for 5 H's. And that would be for X equal to things like the R groups. On the other hand, if X is a group that is electron releasing, something like say a methoxy group or an OH group. So I can draw resonance forms for this. Well, I'll go this way. I can draw resonance forms for this. And in the resonance forms, what I'll see is this. So if I were to draw the hybrid looks like this. So what this means is that the H's that are ortho and para, in other words, the H's that are here and here, are attached to carbons that have high electron density. Those H's are shielded. So what you will get in a spectrum like this is that it will integrate for 5 protons, yes. But what you'll see is a downfield signal for 2 H's and then an upfield one for 3 H's. You get 2 H's here and 3 H's here. So you will get the ortho and para H's as a cluster that is upfield shielded compared to the meta H's, which are relatively deshielded, right? So the ortho and para have high electron densities. They would shield those, the delta value is lower. So this would be about 7. On the other hand, if I have something like a carbonyl group, say I have benzaldehyde, the opposite thing happens. And I'll just draw one or two. I can draw a resonance form like this. And in this resonance form, the ortho and para carbons, and therefore the H's attached to them, are actually going to have a positive charge. Well, I'm going to draw them all. So if I were to draw the hybrid for this one, it kind of looks like that, but the charge distribution is different. So the ortho and para carbons have less electron density, so the H's on them are d-shielded. So I will still get for these 5 H's, but the profile now looks like this. I'll get a set for 3 H's that is downfield, d-shielded, and a set of 2 H's that is upfield. So I can tell the character of the substituent, of the lone substituent, on the aromatic ring. If it's an alkyl group at 60 megahertz, you just see a singlet for 5 H's. But if it's a strongly electron withdrawing group, carbonyl, cyano, and so on, I will get a downfield integral for 3 and an upfield for 2. If it's a strong electron releasing group, I'll get a downfield set of 2 and an upfield set of 3. The last, well, not last, the other one that you would be aware of, or should be aware of, and again this is under aromatic, would be if you run the NMR and you get a signal for 4 H's, you get a singlet for 4 H's. What that implies is you're dealing with a di-substituted ring which is para and symmetrical. So it's called para-symmetrical. Some people say para-sim. And the reason is that obviously it will integrate for 4 H's because I've got 1, 2, 3, 4 H's. But because this molecule is symmetrical here and here, all of the H's are equivalent. So if I call this HA, then obviously there's a plane of symmetry here. This is also HA. But there's also plane of symmetry here, which means this is HA and that's HA. So those H's are all equivalent, therefore I'm just going to get a singlet. So if I get a singlet for 4 H's, I know it is para-symmetrical. On the other hand, if I get a signal for 4 H's, if I get let's just do it here. If I have a para-unsymmetrical, so this is para-unsymmetrical, what would I expect? Well, there still remains a plane of symmetry here. If I call this HA, that's going to be called HA as well. But there is no plane of symmetry here. So I'm going to call this HB, and I'm going to call that HB. So what I will get is HA split by HB into a doublet, as one neighbor, and HB split by HA into a doublet. So technically what I should have gotten is 2 doublets. But because the chemical shifts are so similar, what happens is, so normally 2 doublets would look like this. Okay? And we often call this a doublet of doublets. That's not going to happen.